you should be able to complete pretty much all of your assignments. Yeah, so you'll have time in class for homework today. It's a short lesson. And you'll also have time for to work on your assignment. So what we're going to look at today is we're going to look at infinite sequences, or what we really want to look at is limits as our variable approaches infinity, as x approaches infinity. So what happens to a function as the function approaches infinity? And is there an easy way to determine what it approaches? Okay, so you've covered sequences and series in Math 20-1, correct? Yay, everyone's favorite unit. A sequence is a list of numbers separated by commas in a definite order. So we have our T1 followed by the second term, followed by the third term, all the way to our general term. So the T1 would be our first term, term 1, or we usually call that A. And T of n would be our general term, and that's where we get our formula. Okay. A sequence is often defined by a general term. So here's an example. A sequence has a general term. Now looking at it, is it in the normal formula? Does it necessarily say that it's geometric? No, or it's not necessarily exponential, right? It's not necessarily a times r to the power of n minus 1. Does that sound familiar to you? That formula? Okay. So they give us the general formula. Okay, this is a general formula. So in order to get what the terms are, let's get the first three terms. I'm going to sub in n as 1, n as 2, and n as 3. So subbing in n as 1, 1 minus 3 times 1, all over negative 1 to the power of 1 plus 1. 1 minus negative 3, negative 2, and then we have 1 plus 1 is 2. Negative 1 squared, positive 1. So first term is negative 2. Okay, term 2, 1 minus 3 times 2, all over negative 1 to the power of 2 plus 1. So 1 minus 6, negative 5. And this is going to be an odd power in the bottom. Negative 1 to an odd power is negative. So positive 5. And the third term is 1 minus 3 times 3, all over negative 1 to the 3 plus 1. 1 minus 9 is negative 8. And then again, we have negative to an even power this time. So be a positive 1, negative 8. Okay, so determine t of n minus 1. And that's something you're going to do in inductive proofs in university math, this term minus 1. So let's just practice that. So wherever we see n, what are we going to put? N minus 1. All over negative 1 to the n minus 1 plus 1. So you can simplify this. On the numerator, you're going to bring in the negative 3. On the denominator, if we have minus 1 plus 1, that's going to cancel out. Gives us 4 minus 3n all over negative 1 to the n. Okay, what's an infinite sequence? Well, it's a sequence that goes on to infinity. Okay, if a sequence continues indefinitely, the general term can, but not always, approach a finite value. Okay, so not always will it actually approach a finite value, but it can, which is what that says exactly. So term 1, term 2, term 3, term n. So as n approaches infinity, sometimes, not always, the limit as n approaches infinity for our general term t of n will actually approach some number, L. But the good question here is, why is it sometimes? So how can we tell when that happens? Okay, before we get started on that, let's look at some couple key facts. One, any number over infinity. So if you have a number over a really large number, what will it equal? It's going to get a decimal, really small decimal. In fact, it's going to approach what? 0. And so any number over infinity equals 0. So we're going to use that today. There's also 4 other limits we need to look at. So the limit, if we have a constant, so c is some constant. So think of it as a function. Y equals 2. Okay. So if n is, x is our n in this case, as x approaches infinity, what will our y value approach? 2 still. It doesn't matter. It's always 2, right? It's a constant. And so if we have a constant, the limit as n approaches infinity for a constant is equal to that constant. So if we had the graph, the sequence was 7, no matter what, as our graph, or as n approaches infinity, except for it would just be dots, I guess, natural numbers, it would be that constant of 7. Easy? Because if this was actually a sequence, it would be 7, 7, 7, 7, 7. Get the point? Okay. So it'll always know. Keep going. Okay, so next guy. This is important. All right, so for r greater than 0, 1 over n to the power of 0. So if r is greater than 0, and n is our term number, right? Term 1, term 2, so it's natural numbers. We're not dealing with rationals or anything like that. What will happen if you have n to the power of r? This number here will be really big or really small on the bottom. And we want n approaching infinity to some power of r, which is greater than 0. It's going to be really big, right? Infinity to the power of r is going to be huge. So this is going to approach some big number. So if I have 1 over infinity, or again, a number over infinity, what will that always approach? 0. So if a larger power of n is a denominator, you really get a number over infinity. We're using that equals 0. Okay, so again, n is your term number, so infinity. And if r, as long as it's greater than 0, it's still going to be really large. Yeah, it just makes it a square root, or a cube, right? It's a fraction. It's still going to be square root of infinity. It's still going to be a really large number in terms of infinity, if we think about how big infinity is. Yeah, infinity is a very interesting concept. Yeah, Steve? Why don't we show... No, we have to understand the concept of infinity, because we're actually approaching infinity. So we have to, yeah, this is just a property you need to know. And we're going to base today's lesson off this property, basically. Okay? So next, guys, here's an example. So if n approaches infinity, 1 over n squared, what would that approach? 1 over a large number is going to approach 0. going to be a really tiny number, but it's going to approach 0. Okay, so let's talk about our value between -1 and 1. Okay, so this is a little bit unique. So what kind of numbers are going to be between -1 and 1? 0, okay, yeah. Fractions, yeah. So like 1/2 is an example of an R value. So you'd have like 1/2 to the power of n. So really, if you had 1 or 1/3 to the power of n, what would this approach? Because if the n applies to both of them, well, 1 to the power of anything is 1. And what would happen to the denominator if you have 3 to the power of n and n's approaching infinity? What kind of number would it be? Huge. And 1 over a really large number, that would approach 0. And so that's the case as long as r, if for this property, as long as r is between -1 and 1, it'll approach 0. Oh, right? Okay, so what if our r value is greater than 1 or less than -1? So an example of 4 to the power of n. So let's look at an example before we go to the general idea. 4 to the power of an enormous number would be also an enormous number. So what would it approach? Infinity. Yes. So we could also say infinity, or you could say does not exist. Okay, so the reason why I say does not exist, does it actually approach a specific number? No, it's approaching infinity. It's not approaching some specific number. It's just going to be really large, and it's going to get larger and larger and larger and larger. It doesn't actually approach some constant. Okay, so strategy. What's our strategy? You have to write this in. Sorry, should have gave it to you. Numbers. Okay, so our strategy is this. For infinite rational sequences, so any rational. So how do we evaluate rational sequences? So our first strategy, this is what we're going to do, is we're going to divide the top and bottom of the fraction by the largest power. I should say numerator and denominator as a math teacher, but those are longer words. We all want to shorten things in math. Oh, little side note, which would be good for anyone to hear this, even if it's on the recording. Who taught you math? Seriously. And me. Well, most of you. Okay, I'm saying that as a joke. A lot of you need to work on your equal signs. Okay, if you're writing things horizontally, if you're writing like the limit as x approaches 4 for x minus 4, x plus 4, all over x minus 4. Okay, then a lot of you like to go like this. Okay, where's your equality statement? Oops. Like you just write that. Okay, if you're writing things vertically, that's okay. If you're writing things horizontally, everything you do in math is really a proof, right? I'm proving you the solution, and I'm using true statements to prove the next statement. Please put your equal to signs if you're working horizontally. So many of you, I couldn't imagine, I couldn't believe myself yesterday or today. I'm going through your activities, and a lot of you don't write your equal to signs. Or I also see a lot of, in your limits, you do this. What are you missing? The equation, the function. What are you evaluating? The limit of, as x approaches 7 from the right of what? Right? You have to write either f of x or the actual equation, and then what it actually approaches. So a lot of you didn't put that in there. Okay, couple little things to watch out for your test, because you're going to lose marks if you do that. So I'll give you back your activities, and then you can see if you are one of the many. All right, so moving back to the lesson, sorry, little side note. By the largest power, have to look at the degree. When you evaluate the limit, any expression 1 over n to the r will approach 0. On the side note, you were all really good at writing limit until you subbed. There's very few minor mistakes where that happened, and that was wonderful to see, because in previous years that was kind of the issue. Okay, when you evaluate the limit, any expression of 1 over or a number over n to the power of r will approach 0. Okay, and that's going to help us evaluate the limit. So this is for infinite rational sequences. Okay, so rational, what does rational mean? It's a ratio, or it's a fraction. Okay, so do you see how we're dealing with rational sequences here? Remember the unit of rational equations you did in Math 20? All the factoring? So much fun. Okay, so let's limit. What's the highest power here, or highest degree? 1. So we're going to divide all the terms by that high n, n to the power of 1. So we're going to rewrite this, the limit as x approaches infinity. And so every single one of these terms, we're going to divide them by n. 1 over n divided by, oh no, not 1 over n. Sorry, n over n divided by n over n plus 1 over n. So you divided each term by n, because that was the highest degree. And we could simplify this a little further. Notice I have an equals to symbol. Oh, sorry, this should be n here. Does it say x? Miss Johnson. Really? That's bad. Here I'm lecturing you guys. I can't even have the right variable in there. Okay, let's simplify this. So the numerator would become 1 over 1 plus 1 over n. So now we can actually evaluate the limit, because we could use the property that 1 over n to the power of r, some r value, in this case it's 1, will approach 0. So when we evaluate this, which part of this fraction will approach 0 as n approaches infinity? The 1 over n. 1 over infinity, this is going to approach 0. So our fraction is going to become 1 plus 1 plus, or 1 divided by 1 plus 0, or 1. So this sequence will approach 1. Don't worry, we'll figure out a shortcut in a little bit. Let's do one more, and then we'll talk about the shortcut. So what's the highest degree here? N squared. So we're going to divide everybody by n squared. And simplify it. A lot of you could probably go straight to this step. So if we divide everybody by n squared, we're left with, on the numerator, 1 minus, what does this become? 1 over n all over 2 plus 1 over n squared. And so as we approach infinity, 1 over n will approach 0, and same with the 1 over n squared. So now that we're subbing, we actually get 1 plus, oops, no, it's a minus. 1 minus 0 over 2 minus 2 plus 0 equals 1/2. Okay, is there some kind of shortcut? Well, yes, there is. Okay, so what do you notice about, I don't know if you noticed this, maybe if we did another example, then you'd notice it. Talk to me about the degree of this rational expression, comparing the numerator to the denominator. It's the same. So notice the degree on the numerator is the same as the degree on the denominator. What's the degree of the numerator here? 2. The degree of the denominator is also 2. So if we look at those equal degrees, notice this was 1 and 1, and our fraction became 1 over 1, or 1. Here, if I look at the same degrees, 1 over 2, as it approaches infinity, it approaches 1/2. And so how could we write this? Well, the shortcut is this, that if the top degree equals the bottom of the degree, it's really easy. Okay? If top degree equals the bottom degree, then it's the coefficient, the answer is the coefficients of the highest degree terms. Coefficients of the highest degree terms. That makes life so much easier. So looking at the next one, on the next page, example 3. Oh, for you guys? Oh, lucky ducks. Okay, well, did everyone get this down? Do you want me to wait a second? Sometimes too fast. We're good? Speak up or forever have to go online and look it up yourself. Okay, so this guy, which is on your page, are the top degree and bottom degrees equal of the highest degrees? Yes, so what would this approach? 3 over 8. That was fast. A lot faster. How about the next guy? Oh, these should all be n, by the way. This is a classic case of copy-paste and then not changing the n limit. All right, so are the degrees the same? No. Okay, so let's go back to our old faithful method. Let's divide everyone by the highest degree. What's the highest degree? 7. So n to the 7. Yay. It's a lot of writing. I know this happens a lot in calculus. At least until you get to derivatives, and then it's a lot less writing. Sometimes. No promises. So simplifying that puppy, I don't know what to call him. We get 4 over n squared minus 3 over n to the 5th plus 9 over n to the 7th. And then on the denominator, you'll have 2 plus 6 over n to the 7th. Okay, so evaluating this, what do we get? What would this approach? 4 over n squared. Yeah? No, because we're trying to use the property of a number over n to the power of r. No, r to the power of n. No, n to the power of r. Yeah, n to the power of r approaches 0. But we're actually not going to be doing this every time, right? Because we're going to come up with a shortcut. So you won't have to actually write it like this on your test. You'll be able to evaluate it really quickly in a moment's time. Okay? So what would that approach? 0 minus 0 plus 0 all over 2 plus 0. If you get 0 over a number, 0. So that equals 0. All right, so do you want to come up with a rule right now? What did you notice about our degrees? Top is less than the bottom. So if top degree is less than, I have to write less than if I do symbols. The bottom degree, then it approaches 0. So again, next guy, you might have done something like this in math 20 or 30. Infinite sums. Do you guys do infinite sums of 30? Yeah, so the next two lessons are repeats. It's new in the 30 curriculum. It never used to be there. Yeah. So the next couple days are kind of like review. Okay, so top degree is less than the bottom. What would this guy approach? 0. Okay, last one. Well, last type. Bottom degree is less than the top here, or top is greater than the bottom. Let's divide everybody by the highest degree. What's the highest degree? N to the 5. So I'm going to go straight to simplifying this. We'd have 1 plus 3 over n cubed minus 2 over n to the 5 all over 2 over n cubed plus 7 over n to the 5. So we get, in the numerator, 1 plus, so it approach 0 minus 0 all over 0 plus 0, where we get 1 over 0. Or, can you divide by 0? Does not exist, right? It doesn't approach some number. Which makes sense. If the top degree is greater than the bottom, it's going to be really large, a lot larger on the numerator than the bottom. And so it's just going to approach infinity. So the limit does not exist. So whenever the top degree is greater than the bottom degree, the limit does not exist. Okay, it's not going to approach some number. Basically approaches infinity. So the next example is top greater than bottom. Yeah, so the limit does not exist. And then if you have anything that's not rational, we're just going to generate some terms so you can see, okay, does it actually, let's generate some terms, see if it actually approached some number. So if I plug in 1 here, do I have n again? Nope. We're almost done. We're on the last bottom of the page. You're going to survive. We're almost there. Hang in there, folks. Hang in there. Okay, plugging this in. Can you please get the first term? 1 minus 3 to the negative 1 is 1/3. So 2/3. 10 times 2/3 is 20 over 3. Plug in 2, negative 2. Be 1 over 9. Yes. 1 minus 1/9 would be 8/9. I can do this. 10 times 8/9 is 80 over 9. Yay. You with? Yes? You agree? You checking your calculators? Negative 3 would be 1 over 27. 1 minus 27, or 1 over 27, would be 26 over 27. So 260 over 27. So we're just plugging in n equals 1, plugging in n equals 2, just generating some terms. So this would be term 1, term 2, term 3. So we just sub in n equals 1, 2, 3 to get some actual terms. Okay? So looking at this, do you notice a pattern? What would be the next one? So this is 3, 9, 27. Notice 3's. So it would be 81. And what would it be on the numerator? So 1 less than 80 and add a 0 is the pattern. So 1 less, or the 81 is 80, so 800. Okay, 81 after 81, so 3 to the power 5 is equal to what? I don't know. 125? 243? I'm pretty sure this is 2,420. Yes? Okay, so what do you think it's approaching? Looking at these numbers. 80 over 9, 260 over 27, 800 over 81. What is it approaching? 10. So generate some terms. Okay, you could also do analysis. We could have also taken this and rewrite it as 10 times 1 over 3 over, nope, sorry, 1 over 3 to the n. As n approaches infinity, this here, don't you hate when there's a bracket missing? How would this approach as n approaches infinity? 3 to the power of a large number, large, 1 over a really large number, 0. And so 10 times 1 minus 0 is 10. So we could also use that property. All right. So our review, if top degree equals bottom degree, we take the limit as the coefficient of the highest degrees. Okay, bottom is top is less than the bottom. The limit will be what? 0. Yeah, that's what it sounded like. You were saying. Top degree is greater than the bottom. The limit does not exist. Okay? We're okay? We made it through?